Now it's on. Okay, wanted to talk, that's the title and the program about what I wanted to talk about, the turnpike property in optimal control, and I will talk about the turnpike property in optimal control. But yesterday I came to realize that maybe it would be more interesting, since there are a lot of people here using machine learning inside out, if we adapt the title and rather talk about also turnpikes, also optimal control, but how you can also use it for deep learning. Okay. Let me start with a question to make us all wake up. Who knows what a turnpike is? You know that? What is a turnpike? Yeah, it has something to do with highways, but not with turns on highways, I'm afraid. I'll explain it in a minute. So, but if you don't know what the term means, then you're in very good company, because it's not, I would say, part of the standard English vocabulary. So to explain you what a turnpike property is, I have here an optimal control problem. It's about fishing in a pond, in a reservoir. X describes the fish density in this reservoir. U is the fishing rate. If you look at this model and if you feel like, oh, that very much looks like a logistic function, then you're absolutely right, because that's effectively just a logistic function. There's some extra input for the fishing rate, and this is our objective. What does the objective describe? Well, I'm a control engineer. We always talk about minimization problem, while in economics we very often want to do maximization. The good news is multiplying the objective with -1, we're there. So what we have here is that we have a term minus c times x times u in the objective. X is the density, U is the rate, so this is an amount of fish per time that we take out of the pond times C. So that's what we earn selling the fish. Fishing occurs at a cost. This is modeled by B times U in terms of feeding, labor, whatever, or labor mostly. And also having the fish in the reservoir occurs at a cost. We have to feed them. That's this term. So we want to, in some sense, maximize the revenue we make with operating our little fishing business. These are the parameters. The model itself dates back to 1973. I've stolen it from this book. Now, we solved the problem with techniques that Elena has already roughly mentioned yesterday, and that's what we see. If we start with a low fish density, then initially we don't do anything. We let the fish population grow until at a certain point we start fishing at a constant rate. These wiggles here, these are more or less numerical artifacts, they don't matter here. And then shortly before our time horizon, the problem is over, we start fishing as much as we can. Okay? Now, let's play with the parameters of the problem. In particular, I'm playing now with two parameters, the initial condition and the horizon length in the problem. So I solve it for a slightly shorter horizon, and a slightly higher initial condition in terms of fish density, but structurally I have the very same solution. I let the fish population grow, fish at a constant rate, and towards the end I fish as much as I can. I keep on playing that game, and the only structural change that I can observe is if I start with a high fish density, then initially I fish as much as I can until I reach the very same stationary situation. And again, towards the end, again, I would fish as much as I can. Now, we can ask ourselves, is this a coincidence that for different initial conditions and different horizon length, all these solutions are structurally similar? And it will turn out it's not, and it occurs rather often. And it will turn out that this part in the middle, which is somewhat attractive for all these solutions, is called the turnpike, for reasons I will explain later. Now, why have I put up this example? Well, because the state variable x and the input variable u, or if you like state in action, you could also call it if you're from machine learning, are scalar entities, so we can plot this kind of x-u plane. And what we see here is the following. These curves are the contour lines of this integrand. Okay? So they represent a value where the integrand of my objective functional is constant. It turns out where it's colored red, this is where I can earn most money. The black line, that's the set of stationary operating conditions. That's the set of operating conditions I can find when I set here the derivative to 0. X equals 0 is forbidden. Why? If X is 0, then we don't have any fish in there. This little model doesn't model any inception of fish. There have to be fish to have more fish. So we have to exclude X equals 0. So what we end up with is this black line. This is the set of stable or steady state operating conditions. We don't know yet if they're stable. And what we see here, that's the XU depiction of my trajectories, of my optimal trajectories that I've seen before. If I start with a low fish density, I don't fish at all, then my trajectories literally move along this straight line until in the X direction, they're close to this steady state value of X. They jump literally to this point. You can show that also analytically, that they have to jump, because in U we allow jumps. And once the end of the horizon is near, we would jump here and then would again fish as much as we can, which means we move towards lower values of X in this direction. And if we start at a high density, we would move like this. So what we can already conjecture, that this part in the middle that I've marked by the red dot is not only a steady state, that was already clear by the plots over time, but if you have a sharp eye, you see, oh, this looks very much like the best possible steady state. That's the best possible stationary operating regime that I could find. And somehow the optimal solutions of my problem find this best possible stationary operating regimes automatically, okay? And it turns out this occurs in quite many optimal control problems stemming from economics, stemming from engineering, and we can also use this kind of behavior to design optimal control problems. And when you observe something like this, that this stationary regime, which appears to be optimal in the stationary sense, is attractive for solutions for different initial conditions and different horizons, we call this a turnpike phenomenon. And the classical picture is the solutions move close to the turnpike, stay close to the turnpike, and might leave it again. And what I want to do in this talk today, I want to shed some light on how you can use dissipativity notions, which do not really stem from physics, but they're inspired by physics, dissipativity notions of systems in control to understand turnpike phenomena and optimal control problem. Then I will turn the page and tell you that training of certain classes of neural networks leads to optimal control problems. Then we will see that I can write down these training problems such that they become dissipative, such that they have the turnpike property, which will allow me to give depth bounds, for instance, or to quantify, to analyze what can I expect from an optimally trained network. And towards the end of the talk, I'll show you some results and some real-world data sets. And since I've learned yesterday that MNIST is not a good data set, I also included Cypher 10 results, which will just be submitted this afternoon. Okay, so I'm looking at these optimal control problems. Similar to Elena, I'll go into continuous time. I spare you all the details of in which function space I'll optimize. We can do it with these measurable control or piecewise continuous controls. That doesn't really matter. The classical picture we have in mind is we vary the initial condition, the horizon length, and all the solutions start to cluster, and they may be allowed to leave the stationary operating regime towards the end of the horizon. And an informal definition of this behavior, which we call the turnpike phenomenon or turnpike property, is that the time optimal solutions stay far from the turnpike is bounded independent of the horizon length. What do I mean by this? I make the horizon longer and the solutions stay longer close to the turnpike. Okay? And formally, when we try to analyze this, we will really try to arrive bounds which show no matter what optimization horizon you choose, the time the solutions can stay far away from the turnpike is bounded independent of this horizon. And if you twist this around, it means if I just make the horizon long enough, I will get on the turnpike and I'll have to be there for major parts of the time. Where does this come from? First observations go back to Ramsey in macroeconomics and John von Neumann. So there in the 1928, it's Ramsey, and John von Neumann is 1938, so really, really early. The term etc. was coined in a, I think, rather influential book by Dorfman, Samuelson, and Solow. Note that there are 2 Nobel Prize winners in economics among the authors. And they analyzed linear programming methods for problems in economics, and they explained this phenomenon like this. It is exactly like a turnpike paralleled by a network of minor roads. If the origin and destination are far enough apart, it will always pay to get onto the turnpike and cover distance at the best rate of travel, even if this means adding a little mileage at either end. There seems to be a driving interpretation of their wording when they coined the term turnpike property. And indeed, a turnpike in the US, specifically at the East Coast, is a highway where you have to pay tolls. Here's the Massachusetts Turnpike, there's the New Jersey Turnpike, which connects New York with rural areas in New Jersey. In former times, a turnpike was a toll gate, really a pike that could turn, and you had to pay a fee to keep on moving, okay? But if you think about a highway, or since I'm from Germany, about an Autobahn, that's not too bad. It's kind of an attractive way for the optimal solutions to travel along the horizon. That is how you could interpret that. Okay, this is an informal definition. Let's try to give you a formal definition. And since we're working continuous time, I'm afraid we need a bit of maths. I'm sorry about that. We take such an optimal control problem. Let me decipher this. We look at the following set of times. X star, that's always an optimal solution. Star always indicates optimality for me. And here I take for each point in time the difference of x star to this value x bar. And this difference should be larger than epsilon. And I collect in this set here the set of times when x star is further away from x bar than epsilon. So when this is the set of points in times when my solution is outside of an epsilon tube. Okay, think of an epsilon tube here, and here my solutions have to be outside of the epsilon tube. If we say the solutions of the OCP have the turnpike property, if this set of time points is bounded independently of the horizon length, and if you have to bound a set of time points, in functional analysis, you use the Lebesgue measure on the real line. It's a bit a nasty tool, but you can do that. So you want that for all considered initial conditions, all horizon length, and whatever the size of my neighborhood is, the time I spend outside of the neighborhood, I have a bound independent of the horizon length. Now, two technical details. Either I consider here a compact set of initial conditions, or I have to add here something which depends on the initial condition, because if I move the initial condition far away, it takes longer, literally, to get to the turnpike neighborhood. My way out is always, I say, look, I don't mind if this is a compact set. Okay, that's the formal definition, which appeared, I found it in a book on infinite horizon optimal control, which appeared in the first edition in the late 80s by Carlson, Uri, and Lazarowitz. But the funny thing is, the term turnpike property was coined in 1958. There have been a ton of papers on that in the 50s, 60s, 70s, a super influential review paper by an economist named McKenzie, but there was no formal definition of what is a turnpike property. It was rather as some kind of perception, which you always sometimes find in engineering as well. I know what the property is because I know it when I see it, but no one wrote down this is what we mean. And that is what changed a few years later. Now, here I have drawn the leaving arc. Let me get one point straight. If I have solutions like this, same fish harvest problem, now I consider the quadratic objective. That's why the contour lines are ellipses. And I've now placed the ellipses such that they are centered at some steady state. What do we expect? It doesn't pay off to move away. This typical leaving arc is not there, but these are also turnpike solutions. The leaving arc is allowed, but it's not a must-have for a turnpike. I've constructed here an optimal control problem which literally says never leave the turnpike. Okay, that is completely okay with us, such solutions, because the solutions are now much smoother, but they also cluster here at the best steady state. Okay, now how do we understand these properties? And we understand these properties using a concept, a notion of dissipativity. And we consider here a dynamic system in finite dimensions. You could do that infinite dimensional, you could do it discrete time. I prefer here to work in continuous time. A system sigma is said to be dissipative on some combined set of inputs and states if there exists a bounded storage function and a supply rate such that the change in storage along trajectories is bounded from above by the supply rate. What does this mean? Well, let's forget about this depiction of the system where inputs go out in and states go out. Let's change the system description and say the system interacts with its environment through a supply rate. Think of this as an abstract energy or power supply, which is going into the system, out of the system. This, of course, influences the trajectory, but here it also influences the stored energy in the system. And what this means, well, if you don't supply anything, then the system cannot generate energy, because then S dot, which is here, is smaller or equal than 0. Then the system will dissipate its stored energy. But the energy in the system can grow if we supply power to the system. That is what this literally means. You can look at this as a generalization of Lyapunov inequalities for systems with inputs. Okay? Where does this come from? The idea to work with dissipation inequalities for control dates back to Jan Willem, a Belgian control theorist, which worked a lot of his life in Groningen. And he has coined this in 1972, and that's one of the rare cases where the original paper is still the very best introductory reading you can find. That's incredibly clear even after 50 years. It's an extremely well-written paper. It has 2 parts, and overall it's 80 pages long. So be prepared, but it's really nicely written. And the interpretation is really change in stored energy is bounded from above by the integral over the supplied power. That's the interpretation. If you're familiar with electrical circuits, passive electrical circuits, so where you have capacitors, inductivities, etc., there's a concept called passivity, where you say the supplied power is always the product of voltage times current. That's a special case of this. And Willems was very much aware of this, because he had a training as an electrical engineer, if I'm not mistaken. And he then generalized this. And that resonates with the notion of having a useful description of the first law of thermodynamics and actually also of the second law of thermodynamics for open thermodynamic systems, where you can have energy or information flowing over system boundaries. Okay, what can we do with dissipativity? Now we tailor the dissipation inequality by picking quite a specific supply rate. And we pick now a supply rate where here L, the integrand of my optimal control problem, appears. I subtract from this integrand, which I evaluate along optimal trajectories, the value at a steady state pair x bar u bar. And if this dissipation inequality now in integral form, that's the storage at time t, that's the storage at the initial condition, and the change in storage is bounded from above by the integral over L minus L at a steady state, plus some extra term, which I'll explain in a minute, then we call the OCP to be dissipative in the sense the trajectories it generates satisfy a dissipation inequality. Okay? What is this part here? This part here is what we call in control a class K function. A class K function is a function which is 0 and 0 and strictly monotonously increasing. So this function does nothing else than whenever its argument is non-zero, it enforces the inequality strict. So if you want to have your life easier, instead of alpha of the norm of this, you just write the norm of this with a small factor that's also a class K function. Just says, as long as we're not at this steady state, the dissipation inequality is strict. Literally, this means along optimal solution, as long as we're not at the steady state, this cannot hold with equality. And now what's the interesting thing? If I now plug in here 0 and capital T, the horizon in my optimal control problem, drop this term, then I have here the integral over L of x star u star. So what the dissipation inequality gives me is a lower bound on the optimal performance. Okay, so it is a lower bound on the optimal performance, not an upper bound, which is conceptually a very different thing. If you say you can't get better than something, then you have to be at least as good as something. And that's incredibly powerful to work with lower bounds. Now, what we can find, I will spare you the details of the proof. It's actually 3 lines, but anyway, we can show if the strict dissipation inequality holds, and from all considered initial condition, I have a chance to steer the system to the turnpike, then the optimal solutions will exactly do this. They will steer the system to the turnpike, and I can give you a bound which bounds the amount of time I can stay off turnpike independent of the horizon length. And moreover, I can show, and that's rather easy to see, that these steady states which appear here in this dissipation inequality have to be globally optimal steady states. How to see that? Well, consider this one here at steady state, then x star of t corresponds to x0. Okay, that's easy. So on the left-hand side, I have a 0. And if I'm at steady state, I can throw away the integral as well, end up with this inequality. Now assume x tilde u tilde would be a better stationary solution for L than x bar u bar, then this one here is negative because this would be smaller than this. I do minimization. This would be negative. This is negative anyways, but then I have 0 is smaller than negative number plus negative number. That cannot be the case. That's a contradiction. Even more so, it cannot be equally good. Even if this equates to 0, is 0 smaller than something negative. So what this dissipation inequality does is, in an elegant way, without using any convexity argument, it links the stationary behavior of the system to the optimal solutions, to the dynamic trajectories. And that's super, super powerful and has taken not only me, also other colleagues who work on this, about overall to understand the full picture a couple of years until we understood what's going on. Now, if this result is useful, or this result would be useful, if you can give me a dynamic system or an optimal control problem, I can tell you it satisfies this dissipation inequality. So what I have here for you is a standard benchmark problem on nonlinear control. It's called the van der Voos reaction. A reacts to B to C and 2A to D, but we are interested in A. So our product is something which could continue reacting to other things we don't want to have. How does the reactor work? We have an inflow of resources with a certain inflow concentration of A in particular. So we can control the volume flow rate and we can control the temperature here in the cooling jacket of the reactor. Typically, would model here another linear system because you have a temperature gradient there, but we simplify that. If you write down the partial model just for A and B, then you find these are the concentration balances for A and B. These are the temperature dynamics, and the real nasty bits are hidden in the reaction rates where these exponential Arrhenius terms appear, because how fast the reaction goes depends heavily on the temperature. You have constraints. Concentrations have to be non-negative. Temperature has to be bounded. Constraints on the flow rate. And then the temperature in the cooling jacket. What I'd be interested in is maximizing the amount of product B. I write this like this, and the amount of product B concentrations times flow rate integral over. This is the amount of product B. Now, what I need to check is reachability and dissipativity. I've chosen this model because in a different paper in my PhD, I showed, oh yeah, this thing has nice reachability properties. Essentially, I can see it almost from anywhere to anywhere. So that's ticked off. So the question is how to verify the dissipation inequality. And now, if the dynamics are polynomial, what I can do, I can phrase a semi-definite program of the following form. I want to check for all x and u in my combined state and input constraints that the dissipation inequality holds. Here we have a specific structure for the class K function, but I have to find a description of the storage function S, and I look over the real-valued polynomials. And I can look in this search in this polynomial space and phrase a convex optimization problem that if I find a feasible solution, I have found a storage function. Then what's the catch? I have to pick a highest degree of the polynomials, the set of polynomials I look in, and if I don't find a solution, I don't know anything. And these problems become incredibly harder the larger dimensional the space is. But then I can compute such a polynomial. We did this here using tools which are called sum of squares programming, and we find a fifth order polynomial in the concentration A, blah, 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 a very abstract expression, but we could compute that. Now you may wonder, hey, shouldn't the storage be bounded or sometimes even non-negative? Why is this a fifth order polynomial? You also compute some kind of polynomial multipliers to handle the constraints, and this can lead to odd degrees there, okay? Not only even degrees. So we can compute that. Now that we have the storage function, let's compute optimal solutions, because they should show the turnpike phenomenon. In red, the best optimal steady state. In blue, the open loop optimal trajectories. We see concentration A, concentration B, temperature. They move close to the optimal steady state values. Now we change the initial condition. Same behavior. Observe here these weird things. This is where in the analytic solution most likely measurable controls would appear, because that's indeed again a nasty problem. What I've plotted here, delta, is the residual of this dissipation inequality. So I bring all the terms to the other side and check, do I satisfy my dissipation inequality? And if delta is less or equal than 0, I satisfy my dissipation inequality along the trajectories. And indeed, that seems to work quite nicely. So we can check that. But there is no free lunch. What's the no free lunch here? The no free lunch is that similar to computing optimal value functions, there is a curse of dimensionality. I cannot do this for a system of 500 state variables. It simply takes for ages to solve the numerics. So it's a nice tool, but it's limited in scalability. Now that's why we can ask the opposite or the converse question. If I observe the turnpike phenomenon in the open loop optimal solution, can I show that the system has to be strictly dissipative? And it turns out you can show that. We have done this under the assumption that, okay, for all initial conditions, we have the turnpike at x bar, and then there is a local bound on the cost function which only has to hold locally, and then we can show the OCP is strictly dissipative for optimal solutions. So essentially, modulo some technical assumptions, we can show if the OCP is strictly dissipative with respect to the steady state pair, that's the same as saying the optimal solutions of the OCP have a turnpike. And if you don't like this condition, you can verify this condition with a second order sufficient KKT assumption and some linear independence constraint qualifications on the stationary problem. Then you can verify this one here. Okay, so that's the same. So I don't have to look for storage functions. I can look at my open loop optimal solutions and take this as a kind of very good indication, if not certificate, for my problem to be strictly dissipative for my OCP. What can I do with this? I'll give you here another example, and yet again a chemical reactor, but only two states, bilinear dynamics, bilinear objective. These is state 1, x2, the controls, this classical turnpike thing. But what I plot here as well is the dual variables from solving the open loop optimal control problem. That is the Lagrange multipliers of the dynamics, so to speak. And you see, oh, they also show this turnpike phenomenon. So the turnpike is not only a thing of the primal variable, but also of the dual variables which arise in optimization. Now, how can we make sense of this? That's the optimal control problem I've been looking at, finite or infinite horizon, that doesn't matter for me at this stage. I've shown you that this is very, under the strict dissipativity, very closely linked to the corresponding steady state optimization problem. But I can also take the route that Eleanor has been suggesting to us yesterday, look at the optimality conditions of the P and P. Then I define what is called the Hamiltonian. I have multipliers here for the dynamics and multipliers for the inequality constraints. And then the optimality conditions using this Hamiltonian look like this, with the partial derivatives of the Hamiltonian according to these variables. And now I can take a look at this system of ODEs being at steady state. I find this, which appears to be unrelated to this, but if you're familiar with KKT conditions, then you can show that the KKT conditions of this steady state problem are precisely this optimality system at steady state. So what this shows is that it's not a coincidence that turnpikes are optimal at steady state. It has to happen because they correspond to the steady state of the underlying optimality system in primal and dual variables. And why is that important? Well, because this enables analysis of infinite horizon optimal control, for instance, or design of tailored numerical algorithms. So we have a hell of a lot of structure in there, which we can indeed exploit. Now, yesterday we touched upon model predictive control, and Wolfram was asking me, what the hell is model predictive control? Model predictive control is actually an idea which was reinvented several times since the 1960s. What do? You get information about the current state of your system. You solve an optimal control problem, which means you get a prediction of the input trajectory and the state trajectory from solving the optimal control problem. And then you do nothing else than applying the first part of the open loop optimal input. What now happens in physical systems is that the state trajectory that you see on the system will slightly deviate from what you have predicted. Why? Because your models are never perfect. There might be small disturbances. But then you do it again. You look a finite horizon to the future, apply the first part of it, and so on and so forth. So model predictive control is also called receding horizon optimal control, or you could say it's repeated optimal control. And that has very nice properties. In particular, if you can solve these things here fast. Small remark, if you like discrete time systems, you can do the very same thing in discrete time. It doesn't hinge on working continuous time. It's just something which I have chosen here. And now, what do we do here? We always solve the same optimal control problem again. We have to pick a horizon as a design criterion when we design the controller. But the initial condition of the optimal control problem that's there, that will change. So if all the solutions for different initial conditions of my optimal control problem approach the same turnpike, that should be super, super helpful in closed loop analysis. And indeed, that is what is going to happen. In closed loop analysis, that's the same chemical reactor, and now you see closed loop trajectories. We see, oh, yep, we move close to the turnpike. We change the initial condition. We move close to the turnpike. I add more initial conditions. We move close to the turnpike. So what happens if I can certify this dissipativity, my MPC strategy will automatically extract the best steady state. Okay. Now, if you look sharply, you see here small offsets there. You can see them that the steady state is a bit lower than where we converge to. That's not a coincidence. We can analyze this. This is related to the leaving arcs. I will not dive into this, but I would claim that analysis of these kind of problems is by now fully understood in the deterministic setting, discrete time, continuous time, even infinite dimensional. There's a lot of work around there, and that's why we are so interested in the turnpike phenomenon, because they simplify the analysis a lot, and also the design of the closed loop, of the optimal control problem. Okay, now zooming out, what is actually going on? So MPC is an intuitive idea. And there are some quotes. That is Jan Machowski from the University of Cambridge wrote this in 2000, I think even 2002, not 2004, that model predictive control is the only advanced control method that has already changed industrial practice. And he used this 20 years ago. So it's now more true than ever. Why have I put here SpaceX-like pictures on there? Not because I'm a big fan of the CEO of that company, but rather because each single rocket that SpaceX has landed has deployed an MPC controller. Not some of them, all of them. And what we avoid here is solving the Hamilton-Jacobi-Bellman equation, continuous time, or the Bellman equation, discrete time. So we avoid the curse of dimensionality of dynamic programming. Okay. And you can show that you still get approximately optimal feedback that has also been applied in economics. And the turnpike phenomenon is super helpful. Now, what you can now do, and what maybe some of you are interested in, it's not my core domain, is you can combine model predictive control with RL. And that is what in particular Mario Zanon and Sebastian Gros have been doing since a couple of years with a lot of success. And I want to close this rough tour de force about dissipativity and optimal control with a quote by Jan LeCun, who wrote last August even on Twitter that RL requires ridiculously large number of trials to learn any new task. In contrast, MPC is zero shot. If you have a good world model, the good task objective, MPC can solve new tasks without any task-specific learning. So it's not a competition, I would say. If you have a good model, why would I ever do RL? That completely eludes me, because we can solve these optimal control problems for PDEs, for stochastic systems, for coupled ODEs in rather large dimensions with tools which are open source available, okay? And I think at this intersection, we haven't seen the end of the story yet. There's much more that you can do, also in situations where you have partial models. Now let me shift gears for the second part of the talk, and let me try to tell you how I can use these insights about dissipativity is useful for optimal control, this turnpike property is useful for optimal control, to do deep learning. And when you think about machine learning and my field, systems and control, you always think, what is the relation? And there's one big line of research where we use in systems and control machine learning methods for modeling systems, for approximating MPC feedback actions by training a neural network to mimic the optimization. That was already proposed 30 years ago by colleagues from Italy. Or by using neural networks for identification control of dynamic systems. That was a hot topic again in the mid-90s. And now people do meta learning for fancy stuff. So that has been there since a long time. But what if we go the other way around? Can we bring systems and control ideas to machine learning? And what are our systems and control tools? We have analysis tools, stability, controllability. We have synthesis tools, feedback, feed-forward concepts, computational concepts. And the message is this reverse direction of bringing systems and control tools to machine learning has been there ever since. I don't know if any one of you knows the name Eduardo Sontag. By now, I think Eduardo's in his late 70s, if not early 80s, but he has an incredibly rich track record of super influential works. And 30 years ago, he looked into the controllability and stability analysis of continuous time neural networks. Nowadays, you would call them neural ODEs. So neural ODEs are not an invention of the machine learning community. I will have them on later slides. That's just something which has been there in the systems and control communities 30 years ago. This paper here, Approximation by Superpositions of Sigmoidal Functions, was one of the first papers to propose a universal approximation property for neural networks. It appeared in the control journal, and so on and so forth. Here, a more recent paper where Paulo and Garisfat Abaman have revisited these universal approximation properties with control tools. So also in the inverse direction, a lot of stuff is going on. Okay, so all of you know the three fundamental variants of machine learning: unsupervised learning, reinforcement learning, where the reward is the information that is fed back. But I want to take a look at supervised learning and want to see how I can unleash my control concepts to supervised learning. And I will do this now for classification. And as we had yesterday in the discussion after Martha's talk, classification is much easier because the space where my labels for the data live is discrete. I only have to be roughly correct to have a good outcome. While in regression, my labels, yi, are in a continuous space, which is much, much more complicated. Okay? And all of you have used classification today when you have checked your emails, because your spam filter does exactly this. Now, if you take the machine learning perspective, in particular statistical objective, when you do supervised learning for classification, you're interested in how many data points do I misclassify. So in how many points in my data set am I predicting the wrong label? And that's called the empirical risk. That's how often do I get it wrong on my data. As an optimizations and optimal control person, I'd rather look at supervised learning like, you give me a loss function, maybe that's as simple as L2 error, and you give me some regularization and want to understand how this affects the outcome. These are two very different perspectives, and the question is, can we bring them together? And in particular, the loss minimization here is what you would do in regression, but I could also do it for classification. The question is, what is a good objective to be using here, right? And we always want to have regularization to avoid overfits, or weight decay, you would call it in deep learning. And these are the two competing or complementary viewpoints you can have. Now, what is it that we want to control or that we want to train? It's a neural network in the simplest terms with a very simple architecture. What does a neural network do? It takes a data point, propagates it through a set of neurons, then we have an output layer and gives me an output which can be in different dimensions. Could also model here some more nonlinear functionality. And if I use, for instance, what is called ResNet, then the information state or the state in the hidden layers of the neural network at layer k+1 is what is in the previous layer plus added deactivation. So I've added skip connections, that's how you would call it. And I can model the output as some additional nonlinear map. That's a dynamic system which lives on a finite horizon, namely the depth of the network. You can all trace that back to Rosenblatt in 1958. But the main message is neural networks are dynamic systems. If they are dynamic systems, I'm brute force. I write down an optimal control problem to train these things. How do I do that? This is my recursion over the m layers of my neural network, but observe the subscript I. Why do I have a subscript I? Well, because the initial condition for my recursion, that's the current data point xi that I want to propagate through my neural network. Once I'm at the output layer, I will use this data at the output that is this side here, that's my label prediction, plug it into my loss function and compare it to my reference label in the data set. I'll do a comparison for whatever metric I want to do, and then I will average my loss function over my end data points. So what I have here is a classical optimal control problem in discrete time, where I have an objective evaluated at the end of the horizon. We call this an optimal control slang, a Meyer term, and my dynamics are n copies of the neural network. They differ in the initial condition, but what is common to them is they apply the same weight matrices and the same bias terms. They are the same for each data point. And when I now solve this optimal control problem, what I will train for is these weight matrices and these biases. Okay? Now, if I have it there, I can ask myself, okay, I'm brave. I say training of neural networks is optimal control. Now I can ask, can I unleash numerical machinery? We can do. But more importantly, can I use analysis tools from optimal control to understand how the trained solution should look like? And can I use systems theory concept, optimal control concepts to formulate the training? And I think then it becomes really interesting if we try to bring our insight in how to formulate optimal control problems into formulating training problems. Let me see what we have on that. That's roughly for one data point or recursion we're looking at. If you look at this sharply, this looks very much like an Euler forward discretization. So very simple discretization of this ODE. This thing down here, that's what a celebrated neural ODE is. It's a very hot thing currently in machine learning. It's nothing else than looking at this reverse. So neural ODEs are super closely related to resonance. And again, these kind of systems, even with some extra input here, have been analyzed in systems and control since 30 years. Now, if this is so closely related to neural ODEs, I can write in a continuous time training formulation where I swap here the dynamics for the neural ODEs. Why is that of interest? I do some classic optimal control theory. I can't derive this now, but then I find these optimality conditions. The dynamics reappear, and these Lagrange multipliers reappear. We call them adjoint variables. And they characterize necessary conditions of optimality for this problem. Now comes something interesting. What you need to solve that training problem is the gradient of the objective, or an optimal control slang, the gradient of the optimal value function with respect to the parameters. But if I first look at the gradient of the optimal value function with respect to x, so the states constructed here of all the data, this corresponds to the adjoint variable at initial time. So if I integrate the adjoint variable backward in time, I get this gradient here. Why is that important? This gradient appears if I want to compute the gradient with respect to any of my decisions I have to take for training. So long story short, backpropagation is nothing else than the adjoint equation of optimal control. And the adjoint equation of optimal control was derived by Leibniz, Newton, Lagrange, and Euler. And that was 300, 400 years ago. That's a long, long time ago, okay? The funny thing is, in some papers by Hinton and LeCun, they mentioned the close link, but it has been completely forgotten in the machine learning community, to my understanding. Okay, and discrete time backpropagation, you can trace back to this paper from 1962, because most of the people would look at this in discrete time. Now, we can compare concepts from machine learning to their counterparts in optimal control. I cannot do all of this because that would lead too far and I'm running out of time, but it is interesting to translate these concepts into each other because that offers new insight, and that's what I tried to convey yesterday in the panel discussion. Very often, interesting stuff happens at the interface between disciplines and fields. Now let's do this for the tiniest possible example, and I apologize that it's so simple, but it's nicely plottable, and that's why I like the two spirals data set. Two spirals data is we have the black points, the red points. We want to compute a classifier. So something which tells me if a point is somewhere here in this plane, should it be red or black? We do this with 200 samples. Loss function super simple is just the deviation of xi at the end in the output layer to some reference point where we say -10 is for, I think, a -10 that should be there is the black class, and 10 that's the red class. We train this, we need roughly 9 layers, that is how it looks. So you can do that. You can solve this optimal control problem super easy. But that's not that interesting. Why? Because actually, when we have now understood that we can use optimal control tools for formulating deep learning, we can really ask the question of how to design the training problem. And can this help us to make statements about what is a good depth, for instance, for the network, or a good width? That is actually much more interesting. Let's do that. This is the training problem we have already seen. I will now rewrite it. I hide all these initial conditions in one stacked initial condition x0. So that is part of the training data. All the reference labels are hide in the vector y. That's my reference point. And that's here the training data. My U is nothing else than vectorizations of the weight matrices and biases at each layer. I assume I have an identity output map just for simplicity because it's easier to write down. And then I can rewrite the average loss here as an evaluation of the state of my network in the last layer and in comparison to this data vector y. Now, what I want to have for optimal control reasons is this stage cost. Machine learning, you would call it a regularization. Typically, we would only have some L2 norms on the weights and biases. Now I ask, what would I put there as an optimal control person? I would put much more there than just L2. And that's what I want to show you, what you can put there and how it affects this training problem. Okay? So I now want to design this part in the training problem where I've hidden it all in some compact notation. And of course, I have increased the dimensions a hell of a lot doing so. So for my ResNets, I can observe that the dynamics, if I put here a 0 input, they always stay where they are. The state space is covered by steady states. That's this residual term, okay? Because, and the activation function is 0 at 0. Now what I do is, I use my turnpike inside. Turnpike's optimal steady state. So the first thing before I go any further is I ask, what is the best stationary solution for my loss function? And I can compute that offline. So minimize my vectorized loss given y for some good value x. And here I assume that this set of minimizers is not empty. And now I pick just one of these minimizers. Doesn't matter which one, just one. And I squeeze it into this L2 stage cost here, where I penalize the distance between where is my network currently and what's this minimizer I've chosen, plus some L2 term. What can I do with this is the following. I've chosen this as one of the minimizers. I've used my LQ regularization. I assume I have an exponential reachability property such that I can make this regularization decay exponentially fast, which means is I can steer x to x bar without you permanently going through the roof. U has to come down as soon as I reach x bar, which means x bar is a steady state, which I have for the ResNets. What I now find is that the number of neural network layers that my optimal trajectory spends outside of an epsilon neighborhood of this chosen minimizer x bar is bounded by this. Let me decipher this here. What do I have here? Beta and rho are the constants that appear from this one here. Q is something I pick. I pick Q. And epsilon is a parameter. If I want to make the neighborhood large, I make epsilon large. The bound becomes small. If I want to make epsilon small, I make the bound larger. So I can choose Q and epsilon. And that is nothing else than a turnpike result. But now comes the thing. I can look at that and say, okay, if this is the number of layers that my trajectory can spend outside the neighborhood, what if I pick my network depth larger than that? Then I know in return, oops, my solution has to be epsilon close to one of the stationary minimizers of the loss functions. So what we certify here is the required depth of the network under this reachability assumption. I can give you even a bound on what the loss function has equated to. That's the Lipschitz constant, that's a weight factor, and here's my epsilon appearing. So I can tell you how good the loss is going to be if averaged over all labels. So what we do here is we compute a bound such that my optimal data trajectory is epsilon close, and we still have degrees of freedom in that bound, okay? And it's really just using the same proof techniques that we used for the continuous time turnpikes, just in a different setting and using them more constructively. What's the catch? Well, this is really good. So let's go back to empirical risk. I have to speed up and check the empirical risk. Now, if my loss function is such that I have to steer each data point just close to one of the minimizers, let's say epsilon close, and I can classify correctly, then well, that's perfect, because I can give you a bound for finitely many layers to be in such an epsilon tube. And that's, for instance, what cross entropy and then a nearest neighbor argument would do. So I can show that if I choose my bound as before, then I can give you, under this assumption here that the loss looks like a pan, that I have zero empirical risk. And it's just built in, by the way, how we formulate the training problem. Now, two questions. What about overfitting and generalization properties? What about the tightness of this bound? Is this bound any good? How should I know from this, right? I don't know. So that was, again, two spirals. That was the original training formulation with a loss just evaluated at the end of the layers. Now I do my design, and that's how the trajectories look like. And you see they converge close to the reference values much, much earlier because my training forces them to do so. And now given this solution, I want to verify my bound. And I do this a posteriori on these trajectories. Not a priori, I do it on my trained data. I can do two things. I squeeze in my trajectories and fit for beta and rho. So I estimate a reachability bound. Or I simply evaluated the objective of my optimal control formulation. Then if you massage the problem, you can show that the estimate of the bound equates to this. This has some reasons in the proof. Now I do this, I set epsilon to 1, and these are the bounds I get. Estimated ones, the ones with the value function, and that's a toy problem, and I find here depth with 10 to the power of 3, 10 to the power of 2, and that's when I thought, let's throw it in the bin. Doesn't make any sense because the bounds are as conservative as competing bounds with Lipschitz constants. Now, what's the problem? We use an L2 norm here. And the L2 norm scales super badly if you go to high dimensions because each dimension of the vector contributes to the norm. And if you're just 0.1% off in each component, if I just go to high dimensions, the L2 norm will become large. That's a bad norm to compute that bound. So what we did is said, look, we still optimize in the squared 2 norm. That's nice. Convexity, differentiability, that's super nice. But I use mixed norms to compute my bound. So I use here an infinity norm squared for the state, and for U just a 2 norm because U doesn't scale with the number of samples because U is just in the dimensionality of the data points roughly. And I evaluate this in these norms, and then my bounds become much, much more reasonable. My posteriori bounds between 7 and 10. If I add noise, yes, they become worse, but they don't explode by a factor of 100. So they seem to be still reasonably tight. What's the catch? It's still a toy problem. And that is, of course, then the question, how can we go to larger data sets? In particular, I want to avoid using here these L2 structures in the stage cost. And I can only tell you the gist of how you do that, because who has heard of cross entropy for classification? Okay, you can do very same things with cross entropy. What's the catch with cross entropy? If I compute a stationary minimizer of the standard cross entropy, I push the reference labels to infinity due to these exponential terms, but there's a nice way around it that's called soft cross entropy, where I say my reference probability for a given class is not 1, but a value is strictly lower than 1. And in soft cross entropy, which looks like this, these are my reference probability for each class, and I can compute the stationary minimizers, and what they become is for each class a straight line. You could travel on the line up to infinity, but I've also found an unconstrained minimizer of the cross entropy if I'm just somewhere on the red line, and I find such a line for each class. And I can show this is, again, a strictly dissipative training formulation, but now this class K function is in a distance to a subspace. So it's generalized. The argument in there is a bit more general, but I can use that. What happens if we use that? That's MNIST, and I'll get to Cypher 10. MNIST is rather large. That is conventional training, just rate decay. And we started with 60 layers, then 50 layers, 40, to see what is the minimum depth. And you see, from the 60-layer trajectory, I can't tell you what would be. I can conjecture, yes, maybe a shorter network shows, but almost all happens towards the end. And now we switch to our training formulations with, if you give a more graphical, this picture means you compute terms of the loss function already in between at these skip connections and add them to the loss on the output layer. And that's what you get for MNIST in one shot. We solved it for 60 layers. And if I plot this loss trajectory over the layers, I have very good reason to believe, hey, 10 layers should suffice. And it's not this going back and forth, let's retrain with fewer things, etc., etc. Does this work? And you can think of cropping or pruning here. Does this work for Cypher 10? Then it looks much more complicated because you have convolutional layers. Cypher 10 is much, much more complicated. You need a more challenging structure. And you can find here when we train it like this, and that's something which just goes out this afternoon, you also have these plateaus, but these plateaus correspond to these extra convolutional layers when you reduce the data size in the neural network drastically. But you can still find these plateaus. Pruning here looks very promising, but you could also think of pruning here and then retraining. And that's ongoing research to also give guarantees there and to show that you can also reduce the network size. Or have an educated guess about a smaller network size from just solving once on a deeper network. That is the idea. And with this, I have stayed in time. Incredible. What have I tried to tell you? At the end, we talked about turnpikes and dissipativity in deep learning. And the idea is really that we try to unleash our optimal control understanding on deep learning problems, not in terms of getting better numerics, but in terms of suggesting different training formulations, which we can certify for optimal solutions. You see a catch there, Adam, PyTorch, whatnot, they never give you optimal solutions, they give you suboptimal solutions. So there's a lot of stuff to be done there. But what it already does, it enables us the analysis. We're not yet there for certification. That is the next step. And under the hood, we have really unleashed these turnpike properties in optimal control, where we have this close link between dissipativity and turnpike. And here we use this insight to design dissipative training formulations. That is actually what we did. Where's the journey going? Can we push that further? The other thing, which is more aligned with the second part of the title of this workshop, is can we use dissipativity also for reinforcement learning? I think we see that slowly emerging, but I don't think we have really convincing answers yet, at least to my understanding. And of course, you can ask, dissipativity has this physical interpretation. If you have physical system models or first principles models, how we call them in engineering, which model physics with energy dissipation, can you exploit that? But that's a different talk. And that's all what I have for you. Thanks to all of you and to my co-authors, to the funding agencies, and we will explore that further in a larger project, which will kick off in fall, which is named Active Learning for Systems and Control. Okay, that's all. Happy to be grilled with questions. Yes, please. Never thought I would be afraid of flying microphones.
So regarding these neural ODEs, it's known in the SciML community now that the backward integration is numerically unstable. Either the forward is unstable or the backward is unstable.
That's what we know in optimal control systems.
Yeah, exactly.
Then 300 years.
They've now brought those into neural ODEs. But when you do these ResNets, do you end up with the same numerical instabilities? Because here you're not integrating anymore, you're discretizing effectively kind of like an Euler integration.
Yeah, so if you look at discrete time optimal control does not make the numerical integration issues go away. It's still there. And there are two mean phenomena in these backward integration. One is this instability, the other one is this decay of sensitivity, right? And when we started discussing can we use turnpikes, colleagues more and co-authors on some of the papers said, you don't want to have that. Nothing happens here. That's decay of sensitivity. That's not how it's supposed to look. And it took us a while to understand that we can use this to the advantage and say, let's crop there. But what I would suggest is, if I look, and now I make a very bold statement, and it will most likely tremendously backfire. If I look at the current state of how neural networks are trained, there's a lot of empirics and heuristics with stochastic batch gradients, et cetera, going on. And it's a lot of first order methods, but a lot of tricks that we have learned and developed for extremely complex optimal control problems, how to handle the numerical integration, are not yet there. The core ideas of how we train neural networks, modulus, stochastic batch gradient, and stochastic gradients, that goes back to Robbins and Monroe, 1951. And the other things that is done in discrete time goes back to 1962, if you look carefully. Everything which has happened afterwards in more tailored method for numerical optimal control is not yet in there. Because there are ways of how to handle unstable dynamics in numerical optimal control. That's called multiple shooting, where you integrate over shorter horizons and force the solutions to converge over the iterations. But I'm not aware that anyone would have dared to challenge the big toolboxes by deploying such methods. But there are ways there. But it's not by the discretization that you lose that, or that you would get a way around this. I would suggest, if this really puzzles you, try to take a look, what are the tricks that are applied in numerical optimal control to precisely avoid this from happening?
Those tricks have been applied in SciML.
Okay.
There's quadrature methods, interpolating adjoints.
Yeah, but multiple shooting does something else. It splits the integration domain and allows for discontinuous solutions early on and forces the solutions to converge later on. And that has de facto become the gold standard for most MPC numerical methods, ranging from PDEs to embedded implementations. And also you can do what is called pre-stabilization, which is nothing else than a preconditioning, if you look carefully, which avoids the stability at least in one of the directions.
Okay.
So there are ways of doing that. I don't know what all has been done in the SciML community, but I can tell you in the numerical optimal control community, the progress in solving optimal control problems has been tremendous. And I think it would be interesting to see how you can bring these other ideas to this domain.
Okay. Thanks.
You're welcome.
Hi, I had a question about the dissipativity. Like I saw that yeah, you said that it essentially establishes a lower bound.
Yep.
And I kind of missed how that helps you get the the other properties, like the ones that you found in the example, like bounding the number of layers, like figuring out how many layers there are and stuff.
I haven't shown the proof. Maybe I should have put it.
No, just like
No. Just let me show you. This bound, what actually happens in this bound is that the reachability assumption that we have gives me a worst case bound on how bad I can be, because I can, here, one more back. This one tells me what's the worst case. And this leads to first part, not only the beta, but the beta divided by 1 minus rho. Okay, and that gives me a worst case performance. And the dissipativity helps me to get this second term, because what I can do with the dissipation inequality, if we go back, I have it only into continuous time, but that doesn't really matter here. Just a few clicks back. There we have it. Pull the integral over here. Then you see that's my objective. Okay, that's my objective. We normalize the stage cost, this to be 0. Then you directly see I have the integral from 0 to t over L star dt. That's a bound on my objective. Okay. Now, so that's the objective, and this gives me a lower bound. The boundedness of the storage function means that this difference here will stay bounded, because there's only so much, there's a finite amount of energy in the system. That's what it says. Now you bring also this one to the other side, and then I split the integration between the time points where I'm far away from the turnpike and where I'm very close to the turnpike. And then I can throw away one of the integrals and bound the time points when I'm far away in a smart sense, because there I know this one here is larger than adding epsilon in the argument, so I can bound this from above by plugging epsilon in and multiplying with the Lebesgue measure of these time points, reshuffling the inequalities are there. It's a super simple proof. It's really a simple proof, and I just observe here I have the optimal performance, and here I have a lower bound, and then I use this term. But this term is absolutely crucial. Without that, it doesn't work.
Okay, that makes sense. And then the turnpike property, like what kind of problems have it? Like, is it
All optimal control problems which produce optimal trajectories satisfying dissipation inequalities.
okay?
So it is really modulo some technical proof details. I would say the people working on it who have been doing this would say it's almost equivalent. Lars and Matthias, who did similar analysis in discrete time, they have very different proof techniques, but they also find that this is effectively similar. So if you want to know if your optimal control problem has a turnpike or is dissipative, I would say compute open loop optimal trajectories for different initial conditions, different horizon length, and plot them. Look at them, and then you can analyze that. That would be the first way. But it doesn't need to be here a steady state. You can generalize this to subspaces like we did for the learning with cross entropy. You can generalize it to manifolds. It could even be here a periodic orbit or a strange attractor. The distance that is computed here is always with respect to the infinite horizon optimal attractor. And you can show that this has to be the infinite horizon optimal attractor. And that can, of course, be very different things. Really depends on the flow of your systems that you're looking at.
Thank you.
You're welcome.
Any other questions? Okay, let's close also. And so we meet back at 11:30.